Hello and welcome to podcast number 46. Uh, Hopefully this goes seamless with the previous one. So in the previous podcast, we introduced the concept of free radicals. I want to get deeper into the type of reactions they do. Basically, as I mentioned, if you split a single bond, a sigma bond, into its component elements, component atoms, in a homolytic fashion, meaning they each get one electron, you get two free radicals. We also learned in the alkenes chapter you can break a pi bond and end up getting two radicals, but they won't be two separate compounds. It'll be the same compound. We refer to it as a biradical. This chapter deals with just sigma bonds being broken. So I want to look at generically at first, and then get a little more in-depth into specific reactions. There are not a lot, so it should go reasonably quickly for the chemistry portion. Then we'll stretch it out, a little bit of bioexamples, and then a tiny bit of industrial examples. But for now, I want to start with the concept of an initiation reaction. So we have a compound that has no free radicals. We shine light on it, shine some sort of high energy to break a bond. It'll break in a so-called homolytic fashion, and we'll end up with two radicals. So we call this an initiation reaction. We initiate the radical process. Once we have radicals, then we go on to something known as a propagation reaction. That's a case where one radical is on the reactant side, one is on the product side, but it's not the same compound. So a reacting radical will come take an atom away from a different molecule. When it does so, it'll only take one electron, not both, from the bond, leaving behind a radical in its wake. And then last but not least, a termination reaction, where two radicals combine to form a sigma bond and end up with a single stable molecule. Okay, so this is generic. Let's look at it a little more specifically. So initiation reaction, as mentioned, can occur when we add light to something. So light or some form of high energy will split the sigma bond. It could be a peroxide, an O bond that's very unstable. It breaks into free radicals very readily. It can also be a halogen. So the examples we're going to look at most in this chapter will involve halogens. So I'm going to say XX, and we'll go into more detail what X's are. But halogen bond, let's just consider it between two identical halogens. You add in light, that does it most readily. You can heat it enough to break it, but realistically, light is the more prevalent source. It's why peroxides and other compounds like chlorine, bromine are stored in dark bottles, brown bottles, so that light can't penetrate in to break the bonds. And so we end up with two free radicals, and in solution, they can start reacting with things. It's known as, I mentioned before, homolytic cleavage. Homo, same, they each get one electron. Lytic, it breaks a bond. Okay. Once you get a radical, it's free to start reacting in different ways. So it will break most often the weakest bond in a molecule. So if you have an alkene, the weakest bond is the double bond, or the pi bond of the double bond, I should say. And so this free radical can come in, it can pick up an electron from the pi bond, leaving the other electron of the pi bond to go to the carbon it is not connected to. So in essence, you go from an X free radical interacting with an alkene, generating a free radical. You remember this from what we did in the alkene chapter when we added HBr in the presence of peroxide across a double bond and got antimer-Markovnikov addition. So this is simply addition to a pi bond. We've already seen this one. It actually has a reverse reaction. This can come in, it can break that, and this can go up, known as elimination reaction. Not very common, but still possible. So I want to consider that this addition reaction is reversible. That should make sense because in that chapter we did discuss the fact that addition is the reverse of elimination. When it comes to sigma bonds, we end up with the following. An X free radical, halogen free radical, can pick up an H from an alkane, forming HX and leaving an alkyl free radical. Just like with carbocations, we deal with tertiary being more stable than secondary, secondary more stable than primary, resonance better than all of them. This is known as a hydrogen abstraction because we are abstracting a hydrogen. This R free radical is then free to react with something, and in the case of halogenation, with something we'll look at down the road, XX bonds are kind of weak, so the free radical in R can interact with the sigma bond, taking an X, breaking it in homolytic fashion, and leaving behind an X minus. So we call this halogen extraction because, well, we're extracting a halogen. And in the end, any two radicals can come back together. So we'll talk about different ways it can happen, but the X and the X that we made in initiation can come back together, or potentially an R and an X floating around solution come together, or in some cases, even an R and an R can find each other. So it's any two radicals coming together to form a sigma bond and no radical, or if you will, possibly even a pi bond. But that's usually a case of a biradical within the same molecule. Okay, a lot of information being tossed at you. The big thing, the key thing you need to take home from this is no free radicals, two free radicals, known as initiation, propagation 1 going to 1, termination 2 going to none. You reform a bond in termination, you break a bond and form radicals in initiation, propagation just keeps it going. Most of our reactions are going to be a very brief initiation, long ongoing propagation until finally termination stops the reaction. So we're going to look at specifically free radical halogenation. And one last thing I want to mention, just that popped up as you saw, coupling is the process of two radicals coming together. Okay, so let's start with chlorination. And we could have started with bromination, could have started with iodination, could have started with anything, but just going to choose chlorination. So here's my overall reaction. I want CH4 to react with Cl2. I want to put a little light in to initiate it. And I want to put a chlorine on the methyl. So I'll get a CH3, a methyl chloride, and HCl as a product. So initiation. For those of you who maybe aren't familiar with this term, that represents Planck's constant times frequency of light, represents the energy of light. We use it as shorthand for light. So you may also see H nu. So the Greek letter nu represents the frequency of light, HF, also frequency of light. I prefer H nu, but chances are from your GChem experience, you dealt with HF. So could be either one. Okay, we add light in, we have initiation reaction, we generate two chloride free radicals. Then come the propagation steps. Two propagation steps, we saw them on the previous slide, and that was chloride free radical is going to abstract a hydrogen, so it's going to come in, break one of the CH sigma bonds. They're all four equal, so that's what we chose this one. So it's going to take one of those H's, doesn't matter which one. When it does, it's going to leave behind a free radical on the methyl and its weight, and going to generate an HCl. That methyl free radical, that R, is now free to attack a Cl, the weakest bond it can find. And when it does, it can come in here, take one of the Cl's, form a CCl bond, leave behind a chlorine free radical. Sorry. So a couple other things that we should consider. You should consider this radical's ability to react with anything in solution. So I'm showing it reacting with this CH4. It could also potentially react with the Cl2. So Cl free radical reacting with ClCl would give you the following. This radical would go in the form of bond here, that'd go there, and you would end up with the absolutely pointless reaction of Cl free radical reacting with Cl2 to form Cl2 plus Cl free radical. So we generally ignore that, so I'm not going to consider that one. The Cl free radical could also potentially react with the product. And right now, we have way more of the methane and Cl2 than we do the products. But over the course of the reaction, you start getting the Cl free radical possibly reacting with this, taking off the second H, going forward, or taking off the Cl, sending it backwards. So those, again, become kind of unproductive reactions, or they become complicated side products. So for now, I'm just going to consider Cl2 reacting with CH3 free radical and Cl free radical only reacting with CH4. Those are the only two propagation steps. You'll notice when we add them up, the propagation steps always add to the net reaction. So if I were to add these two up right now, the Cl free radical cancels there, methyl free radical cancels, and I'm left with CH4, Cl2, methyl chloride, and HCl. Okay, so the propagation steps add to the overall process. And once you get to a certain point, termination is going to just naturally start happening. As mentioned, you can have just a reverse initiation. two Cl free radicals can couple together, form Cl2. You can also get two methyls coupling together, and you can get CH3Cl coming together. Any of these will terminate, get rid of the free radicals, and reaction stops. So because of this reaction right here, this little side note, we have industrial processes where we refine oils by adding in light and doing it at high temperature, so these radicals start breaking and reforming different sort of hydrocarbons. So we can take very thick, heavy oils, refine them into smaller, more lightweight fuels that we can use. The refining process is also known as the cracking process, where we make free radicals and they literally just go through this crazy combining mechanism pathway to eventually get to a point where you have large, long chain carbons turning into smaller, more usable carbon chains. Okay, so that's our chlorination. Again, want to note the sum of the propagation steps, the hydrogen abstraction, followed by the halogen abstraction. Again, they combine. So the ones that cancel, methyl free radicals and the chloride free radicals. Chlorine free radical, I should say, all cancel and you end up with the same overall reaction you wanted. Okay, so also mentioned that there is an outside chance that chlorine free radical can react with the product and take off another H, add a second chlorine. And this all comes down to stoichiometry. So if I were to add just one equivalent, I will get mostly one Cl on there and some side product of 2, trivial amount of 3, and probably not even detectable amount of 4. If you add in a 2-to-1 ratio, then you can get it to go to methylene chloride with some impurity of methyl chloride, some of chloroform, some of carbon tet. And so it all depends what you're trying to get, but stoichiometry of the reactants will ultimately dictate what you end up with in this process. So if you add 1-to-1, 2-to-1, 3-to-1, or 4-to-1, you can get the majority of the product being 1, 2, 3, or 4 chlorines on the carbon. Okay, that's an overview. Want to look at it in a little more detail in terms of what's actually happening. So the reason we break the Cl-Cl bond or the halogen bond is it's the weakest in solution. So if you put light in, give it barely enough energy to break the weakest bond, then you can control the reaction to some extent. So let's consider the energetics, the delta G equals delta H minus T delta S. We shine light on this system. We get the HCl and the methyl chloride. 2 reactants, 2 products. So delta S, no rings, no pi bonds, no real complication with sterics, 2 atoms, 2 atoms, 5 atoms, 5 atoms. It's pretty much the same thing. So as far as delta S goes, essentially 0, which means delta H is essentially equal to delta G. So delta H can be found, and consequently so can delta G. But I'm going to use the delta H approach of energy of the bonds broken minus energy of the bonds formed. So we're revisiting chapter 6. If I have this HCH bond being broken, the CCl bond being broken, CCl bond being, or ClCl being broken, CCl being formed, HCl being formed. Looking up in a standard table of energetics, methane CH bond is around 439 joules per mole. I should say kilojoules per mole. 238 kilojoules per mole for ClCl bond. 359, so it's not as strong a bond as a CH bond. HCl 427. Okay, so I have these different bonds, and again, it's broken minus formed, always alphabetical. So broken minus formed equals delta H, energy invested into the system. So the system is gaining energy. You put this energy in to the chemicals when you break them, so it's positive. This energy is released when the bonds are formed, so this is negative. So this plus this minus this one minus this one. So delta H reaction, 439 plus 338, minus 359 minus 427. Combining it, excuse me, we get our 677 minus 786. So negative 109 kilojoules per mole. I'm going to hang on to that number in my mind. That's a pretty decent amount of energy per reaction. Okay, let's consider all the halogen reactions. So we had negative 109 for chlorination. We did this with fluorine, same 439. Notice HF bond is much stronger. And FF bond, weird as it may be, this is a naturally occurring pi bond without a sigma bond. The way these overlap, It's actually considered to be a pi bond between the two, which makes it extremely weak. So very weak bond forming a very strong bond. You can probably guess which way this is going to go. So these two added together, we get 593. These two added together, we get over 1,000. We get 1,015. So 593 minus 1,015, you end up with negative 422. Bromination, same thing, 439. This is going to be a little weaker than the HCl bond, but not much. This is weaker than ClCl, so I invest a little bit less. I end up getting, though, notably less for this bond. So it ends up, it's barely exothermic. Then iodine is very weak, but these bonds are very weak. So it ends up, what I'm gaining is so little, it doesn't make it worth breaking the CH bond of methane. Okay, so putting it in perspective, reminder, the Cl1 was again negative 109. So as I go down the periodic table, I go from negative 422 for fluorine, negative 109 for chlorine, negative 28 for bromine, and positive 51. So I'll just put that there, periodic table. 4 elements we're dealing with. We'll give you negative 422, negative 109, negative 28, positive 51. A couple of problems hopefully you spot right away. Negative 422 is pretty much enough to break any bond here with the exception of CH bond, and it's really close to doing that. Meaning if you generate something where you create enough energy to break another molecule almost instantly, that means the reaction is going to go and trigger another one, trigger another one, with a pretty severe problem, and that is an explosion. Way too energetic, it's impractical. This thing will blow a building up. So fluoridation, kind of impractical, so we don't do that one. Bromination, slow but favorable. Iodination, it's positive, which means it's unfavorable. You'd have to pump energy in, and you don't really gain much unless you desperately need one of these molecules. You suffice to do Br and Cl. So this might explain why in the previous chapters, when we'd present the book, or I would present different alkyl halides to react, notice we almost always went with RBr or RCl. Rare occasions we go with Ri. It's not that it isn't reactive enough, it's that it's too hard to make. So bromination and chlorination are your more common ones. So this one being positive, it's not going to do anything. It's just going to be dead weight. So chlorination is going to be a little bit faster than bromination and favorable. So this one, iodination impractical, fluorination explosive. So chlorination and bromination. Notice that chlorination is fast, bromination is slow. The slower you go in general, think of anything you've ever done, go shopping. If you shop methodically and slowly, you generally buy everything you're supposed to get. If you go too fast and you're careless, you sometimes come home with the wrong product. You pick the wrong shampoo, you pick the wrong peanut butter, pick the wrong something. So we make mistakes when we go too fast. We're not as selective. So the word selective is going to kick in. Because this is slow, bromine is very selective for the most stable CH bonds, or the most stable compounds after replacing CH bond, I should say. And chlorination, not as selective. So that'll make sense hopefully soon. Okay, so fast and favorable. Let me get rid of that. Shoot, fast and favorable sounds like it should be a movie series with about 9 versions. We only do chlorination, fast reaction, bromination, slow reaction. We do not do iodination unfavorable, and we do not do building blower upping things. That came out so bad. But we don't do fluorination because it's explosive. So I mentioned we used HV, light. So now I've changed from HF to H nu. Hopefully you still recognize it as light. Or we can initiate it with peroxide. So a lot of our polymerization reactions will trigger with peroxide, put lead on peroxide, peroxide will break, form free radicals, which initiates a reaction, and you get this long, I guess, polymerization where one monomer reacts with another, and it very, very quickly forms a long compound, long fibrous compound. One thing about that, I mentioned it briefly in class, that dentists do fillings through this process. And so it's a really cool evolution. So I guess they discovered it in the 60s, but it didn't really get used until roughly the mid to late 80s. And took UV light, so it really was impractical, but they put this polymer slurry, this monomer slurry, just these molecules, painted onto a tooth. They'd shine UV light on it. It'd start to polymerize, you'd form plastic. They'd add more of it. They'd shine more light, and you'd basically build this plastic coating. And then they'd shave it down in the right shape that they needed it, and they were plastic coating kids' teeth. It sounded great, except for one small problem. These polymers would eventually crack, and it started trapping food in with the teeth. And so rather than protecting them, it actually formed as this little pocket to hold all the basic decaying material. And in doing so, it actually made things worse. So they stopped doing that process, but they kept up with the fillings. They use it still for fillings. That evolved. Somewhere in the 90s, they made it a violet color, so it was a little more user-friendly. You didn't have to have a UV light and worry about looking at a UV light. And then nowadays, they actually go to blue. And so, interesting fun fact, but if you've ever seen a dentist at work and they have that little blue LED light, there's a little orange circle there, which basically just filters out the intensity of the blue. So if you recall, an orange filter, the opposite on the color wheel of orange is blue. So something looks orange because it's absorbing blue and reflecting orange. So if I have an orange filter, it absorbs all the blue so that light doesn't come through as a dentist and strike me in the eyes. So fun little fact, but polymerization also done with a slurry in incident light. Okay, fun fact done. So the energetics, as mentioned, chlorination, very large delta G, -109. Bromination, not so much, -28. The other thing, the activation energy, it's kind of exaggeratedly small. I'm taking this from the book, and I really shouldn't. I should look at it more carefully. It's actually going to be more energy than that. But the point is, it's still less energy for chlorination to get going than it is for bromination to get going. So it is highly unselective. Chlorine will react with anything, whereas bromine prefers to form the more stable free radical intermediates. So it wants to form something a little bit better than chlorination. So fast reaction, not selective. Slow reaction, highly selective. I will pick up selectivity in the next one, but hopefully that's sort of a lead-in. So that's halogenation. It's going to become math pretty quick, but we will get to it when we do. So thank you for tuning in, and I will see you at the next podcast. Bye.